So window is this one. Okay, can you see my slide? Can you view my slide?
Can, sir.
Yes, sir.
Okay, okay, good. Alhamdulillah. Yeah, normally in a normal class you are not allowed to eat, but you can drink. But now you can eat and drink. Enjoy yourself. Right. Okay. So the first lesson is on introduction. We will look at some basic principles, yeah, that we need to understand in order for us to be able to understand how electrical machines work. So there are a couple of a few things in here. We look at the rotational motions. Yeah, it's basic physics. Surely most of you, all of you, have come across this before, yeah, in your SPM or your A levels, yeah, or something equivalent to this. Then you would have studied this, and also then we look at the magnetic field theory, the fundamentals. Again, surely at least most of it you have covered before. Okay, after we go through some this magnetic stuff, we look at the energy losses in ferromagnetic core. Yeah, ferromagnetic core is a very important element in electrical machines, be it a transformer, a motor, or generator. They all use ferromagnetic core. Yeah, and finally, we are going to look at the real, reactive, and apparent power. So different types of powers in AC circuits. In DC circuits, the power is simple. Yeah, you've got basically only real power, but with the AC circuits, there are different types of powers. And then again, we are going to look into this one by one later on. Right. So, okay, let me do it like this. Okay. So, what is electrical machine? Okay. Generally, electrical machines are devices that convert electrical energy to mechanical energy, or vice versa. So, depending on what you're referring to. So, which one is motor? Electrical to mechanical or mechanical to electrical?
Electrical to mechanical.
Yes, it is. Yeah, it's electrical to mechanical. I cannot see the chat box while I'm presenting this. Yeah. Okay, when you answer, I think it's better to use voice rather than typing because I'm not able to see both screens at the same time. Okay, yeah. So motors, correct. Motors is converting from electrical to mechanical. Yeah, and that's why when we use motors in the toys, for example, you connect it to a battery, and then which is giving electrical energy to it, and then it will start rotating, yeah, which is producing mechanical energy. Not really producing from nothing, but it's actually converting from the electrical energy as the input, and the output is the mechanical energy. Yeah? And generator is the opposite. It's the other way around. You give it mechanical energy, yeah, and then it will convert it to electrical energy. Okay. The other type is transformers. How about transformers? What is the input? What energy is the input?
Electrical.
And the output?
Electrical.
Electrical as well. Yes. So why do we want to use transformers then if the output and input are of the same type of energy?
Suitable amount of voltage, current.
Yeah. Okay. It's good. Thank you. Yes. So you can adjust, yeah, the input. You can, for example, the voltage, you can step it up or you can step it down, yeah, depending on the requirement of the system that you want to power, yeah, with. Okay. Okay, then and that's why although the input and output are of the same type, we still need the transformers because it's still giving us some usage, yeah? Some useful things or useful functions. Okay, and okay, here they are, the different types of electrical machines, motors, generators, and transformers. And again, all these things, especially the motors, are very important elements in mechatronic systems. Yeah. Most mechatronic systems will use at least one of these, especially the motors. Yeah, as I said. I don't have the circle. If you remember, there is a circle when you represent a mechatronics. Yeah, there is a hardware there, software. What else? The three main circles. You've got the, I forgot now. You've got the control or the software. Okay, you've got the sensors, as you have the actuators as well. Yeah, the actuators, as I mentioned in the our first briefing last time, most of it will be using motors. Okay, and again, the motor convert electrical to mechanical, generators doing the other way around, and transformers just like you have mentioned that it will convert from electrical to electrical, but of different levels of voltages and currents. Yeah. But the reason why the transformer is included, as it's stated here on the slide, that because it's working on the similar principle as the other types of electrical machines. Yeah, which is this based on electromagnetic energy conversion. Okay, and what's next slide here? I cannot. Okay, see. Okay, right. For this slide, yeah, because you already have the slide, so no need for me to hide them. Yeah, if you look around you and if we in our daily life, yeah, uh, apart from motors, electrical motors, you will see other types of devices that will also generate uh, or have mechanical energy as the output. Yeah, that will create motion as well, which is the car engines basically. That's probably you don't see it, but you see that the cars are moving. Yeah? And these cars are basically using this internal combustion engine or ICE. Yeah, it can be of using petrol or diesel engines, right? And this is still the most popular modes that you will find on the roads. Yeah? Some cars, I mean, the more advanced car already use hybrid, yeah, or maybe purely electrical, but most of them are still use this type of engines, this ICE engine, internal combustion engines. Okay, so there is similarity between ICE and motors. Both of them generate motions. Yeah. Okay, however, despite the popularity of the internal combustion engine, still many applications are using electrical machines, yeah, because it's not always practical to use internal combustion engine. For example, if you have a fan in the house, can you imagine if you have to use ICE for the fan? It's not really practical. It will be noisy, yeah, at least, and then it might it has some emission, yeah, and so on.
Exhaust.
Yes, from the exhaust, exactly. Yeah, so it's not practical at all, and
No.
that's why, yeah, as well, the latest trend is that you are even for the cars, you use the electrical motors as well, yeah, because yeah, when we talk about emission, pollution, green technology, then electrical machines are generally considered as more green technology, okay, more friendly for the environment. Although the mathematical equations are not that simple, yeah, because the electrical it will also depend how the energy or the electrical energy is created. If the electrical energy is created by using a coal power station, example, then yeah, this coal it also emits pollution. So the amount of pollution might not be less in that sense. Yeah. Also, when you make all these motors and things like that, the manufacturing plants also will emit some gas that is not friendly for the human beings and for the environment as well. So all this involves some lots of things and parameters to be considered before we can decide. Okay, this technology is more green, is more friendly, more environmental friendly. But one thing for sure that when we use the electrical vehicles, at least, for example, if you use it in KL, then the pollution in KL will be less. Yeah, the power plant might emit what they call unfriendly gases, yeah, but it's far away from KL. Yeah, so it's far from the urban areas. That's one thing for sure. So that's why, at least for that, from that point of view, we have the benefit. So for the areas that are have more population or populated by more people, we can reduce or even like yeah, reduce significantly the amount of emission in that area. That's the benefit of using the electrical machines. Okay, and in addition to that, also the efficiency is higher. Combustion engines got efficiency only about 40%, while electrical machines you can get up to above 90%. Okay, so the first thing now we want to see is the rotational motions. Yeah, just quickly, it's not going to be very deep. Yeah, again, we need to understand about this as a fundamental knowledge, so that we can understand better about how electrical machines work, and we can also do the analysis of, for example, how do you count or calculate the required torque for a given application. Yeah? Somebody came to you, your customers maybe, or your clients, and ask you to design a system. They give you the specs, and then you need to decide which motor is suitable for that application. Yeah? So we might need to do some calculation. Yeah? Also later on, I mean, even during your study here, there will be very likely that you will be involved in some sort of calculation in determining the which motor is suitable, yeah, for your project. And then you need to show the calculation. Yeah, you cannot just this is the difference between an engineer and a hobbyist. Yeah? And a hobbyist might just take the approach of trial and error. Yeah. Okay, so with blind guess, they okay, and probably just go to the shop and they just find whatever motor is there, then they buy it, and then just test it. If it's not working, then they try another one, maybe a bigger motor if the torque is not required, it's not enough, and so on. But for engineers, you need to do some calculation first. In nowadays, obviously you have software as well. Yeah, you have software, you have modeling software that can help you as well. But in depending on where, if you are working in a company, some companies are not rich enough to buy the software, then you need to do a hand calculation. Yeah, so more manual. But in bigger companies, then yes, they may be able to buy the software. Okay, like MATLAB, for example, is very useful. MATLAB with Simulink, when it comes to calculation for this kind of system, is a very useful one, but it's very expensive as well at the same time. Okay, right. And then why rotational motion? Because most of electrical machines are rotating about an axis. Yeah. Okay, so it's very important to understand this. And the good thing for us, yeah, in general, a 3D vector is required to describe a rotation of an object. But since machines rotate around one fixed shaft only, yeah, only one fixed shaft, and that's why then we can just use one angular dimension analysis. We don't need to do three-dimensional analysis. Yeah, so this makes our lives easier. Okay, if you have any question, if you want to stop me, and you just give me a shout. Yeah. Right. I tried to be not going too much details. Yeah. Okay. For rotation motions, there are a few terms, technical terms. Again, surely you have come across this before. First, the angular position, and the symbol for it is theta, and it's measured in radians or degrees. Yeah. Okay. At this point, I would like to remind you, as engineers, please have a discipline of writing down the units, yeah, every time you write a number in, yeah, be it in your report or in your exam, yeah, and so on. Yeah. So because numbers can mean anything. If you say that theta is equals to 2, what does 2 mean? Is it 2 radians or 2 degrees? Yeah. So be very careful, and please develop the discipline of always writing the units. Yeah. Okay. In exam, this can for if you miss to writing the units, it may the examiner, yeah, or the lecturer may mark you down for it. Yeah. Especially if you already get very high mark, then we need to find somewhere that you make mistake. No, but yes, seriously, as a discipline, you need to write it down. You know, especially later on, if you work internationally, you have partners in the US, you have partners in the UK. Yeah, these people can use different systems, and if you don't write the units, it may cause confusion or even a, a very serious problem. Yeah, if you look at, if you Google it, you can find cases with even when they're sending some rocket, or what we call like space shuttle to the outer planet, and because of the misunderstanding of the unit, the project have failure. Okay, and then angular velocity omega, and as you can see here, there are few different units again being used. Yeah, radian per second, revolution per second, revolution per minute, or RPM. So there are different units. Although people use different notations, different symbols. Yeah, omega m, for example, when you use the radian per second as the unit, and nm when they use the RPM. All this refer to angular velocity. Okay, and then angular acceleration, yeah, which is the time derivative of the omega or angular velocity, and the unit is radian per second square. Yeah. Okay, the angular velocity is d theta by dt, and the angular velocity is d omega by dt. Yeah. So omega m, or the angular velocity, is the time derivative of the change in the angular position. Okay. Can you answer? Can you try to do this calculation and answer the first one? Per second, what is it in RPM, which is revolutions per minute? You try it, and you can type your answer on the chat box.
The first one is 600 RPM.
600. Okay. Any other answer? Muhammad Hafizuddin also got 600. Okay, yeah. So how did you get 600? How did you get 600? What did you do with the calculation? How did you calculate it? Or anyone else got a different answer? This is okay. I've got the camera and the screen at the same laptop. So see if I can write it down here. So you got 10. Oh, yeah, it's not very nice position. It's very difficult to write. Okay, I will try anyway. 10 revolution per second, yeah. Because we need to convert to revolution per minute. Okay, RPM. Yeah, this is RPM. So you got revolution per minute, right? So the revolution stays the same. It's just the S, which is second, we need to convert to minutes, right? Okay, 1 second. How do you convert second to minute? What do you do?
60 seconds.
Yes. 1 minute is 60 seconds. So 1 second equals to 1 over 60 minutes. Yeah.
Yes.
Okay. So from here, you can substitute S, yeah, with 1 over 60 minutes. So you've got 10 revolution over 1 over 60 minutes. Okay. So from there you can get this by using this information, the equation that one second is equals to 1 over 60 minutes. Okay, then for this, from this you can see this will go up here. So you got 600 rev per minute. Yeah, and this is how you get the 600 revolution per minute. Okay. Okay, how about the second one?
60K.
60K. 60K.
Yes.
Yes.
Are you sure? Check again. I don't think so, but I'm guessing. I haven't checked it, but it doesn't seem to be revolution per minute to radian per second.
16.66.
16.66. Okay, it looks like that's the answer. Yeah.
16.67.
What is it?
16.67. We rounded up.
16.67. Okay, it's probably more accurate than the the first one, but it's very close. Yeah. Okay. Yeah, I think those answers are correct. Yeah, 16.67 is a more accurate answer. Okay, how do you get this one? So 1000 revolution per minute. Revolution per minute. And the revolution you need to convert to radian per second, to radian. Yeah. And the minute you need to convert it to second. One revolution is 2 pi radian. So you need to multiply by 2 pi. And minute is 60 seconds. Yeah. But because minute is the denominator, not the numerator, yeah, at the bottom, so it effectively we are going to divide it by 60. Yeah. So 1000 times 2 pi over 60. Yeah. Okay. What do you get? Is that correct? 16.67? 2 pi 6. No, both are wrong. It's close to 100. Yeah. Anybody got calculator?
104.72.
104.7. Okay. So this is the answer. How did you get?
I forgot to. I thought that one is.
Oh, yeah. You only divided by 60. You didn't multiply by 2 pi. Okay. Yes, sorry, I was wrong as well. So this is wrong.
Okay. Sorry,
Okay,
sir.
so no, it's okay. It's good attempt. Okay, they look simple, yeah, but as you can see, we can easily make mistake. Yeah. Before I came to UIA, I was working 8 years in industry in the UK. This kind of thing even caused us headache. Yeah. We had this just to solve this kind of problem. And as you can see, we easily make mistake. You need to multiply by 2 pi or divide it by 2 pi, multiply by 60 or divide by 60, easily can make mistakes. So be careful, although it's simple, but be careful in carrying out this kind of calculation. Yeah? Okay, but I think you all understand the principle how to do this calculation. Let me know if you have any question. Okay, next. And also this actually, yeah, this also required in doing the analysis later on. So even important in your exam as well, the knowledge of doing this type of calculation. Right, okay, and now what start? Okay, let me just check the timing. 12. Okay. Right, linear motion. Right, okay, we are basically, when we do this rotational motion, our understanding about linear motion is important or useful. Okay, I should say useful, I think. Yeah, probably most of us remember more about the linear motion than the rotational motion. Okay, when so that's why if we understand the linear motion, if we remember it, the equations, yeah, then it will be easy for us to derive the equations for the rotational motions. Okay, in linear motion, a force is when a force is applied to an object, it will cause the velocity of that object to change. Yeah, it can be acceleration or deceleration. Yeah, depending on the direction of the force and the direction of motion of the object. Okay. Can you give me example that a force can decelerate an object?
Frictional force.
What is it? Sorry?
Frictional force.
Frictional force. Yes. Okay, that's good. Good. Yeah. So frictional force, such as what? If you are pushing a table, yeah, and then you stop, you push the table, yeah, with your hands, then you let your hands off the table will not move very far. Depending on the frictional force, it will eventually stop. Yeah, whether it's by after a few millimeters or a few centimeters, depending how the roughness of the surface, which determines the frictional force. Yeah. Okay, so yeah, that's a good answer. And again, will be very relevant to later on when you design robots or things like that, yeah, that moves on the floor, and you will need to know in some cases, yeah. But generally, when we talk about robots nowadays, we just buy it. But yeah, probably there will be some project for you later on to determine, to calculate or to know the frictional force and then determine the torque required from your motor. Okay, yes, so force is not always accelerate, but it can also decelerate. Yeah, again, depending, yeah, when we talk about the friction, frictional force is the opposite direction to the motion, and that's why it will decelerate the motion of the object. Right. Okay, when that's in linear motion, when it comes to rotational motion, we will have a similar concept, which is torque. Torque will also change the velocity. In this case, particularly angular velocity of an object. It may cause angular acceleration or angular deceleration. Yeah. Now, when the torque is zero, when the net torque is zero, total torque is zero, then there are two possibilities. The system is not rotating at all, i.e. the angular speed is zero, or it rotates at a constant angular speed. Okay, so when the torque is zero, it doesn't mean that the object is always static. It may be rotating, but at a constant angular speed. Okay, and again, this concept is very important for us later on when we do some analysis of the motion of electrical machines. Okay, and this is actually applies also to linear motion. Yeah? When the force is zero, either the object is stationary or the object is moving at a constant speed. Right, and what is a torque? Torque on an object is the product of force applied and the smallest distance. Yes, the smallest distance we need to underline this is the smallest distance between the line of action of the force and the object's axis of rotation. Yeah, so it's not any distance, but it's the smallest. Yeah, the smallest distance between the line of action of the force and the object's axis of rotation. I think we've got the illustration on the following slide. Okay, so for the first one on the left hand side, the torque is zero. Why the torque is zero? Although we have force there, we have a force, and it's applied to the object, but the torque is zero. Why is it?
Not rotating.
Yeah, but why not rotating? We apply some force there, but why is not rotating?
Because of applied at the center.
Yes. Okay. The force is pointing toward the center, yeah, which is based on the definition that we had on the previous slide. The torque, yeah, is the force times
Distance.
the smallest distance. And what is the smallest distance here? Because this is the line of action of the force. So what is the smallest distance between the line of action and the axis of rotation?
Zero.
Exactly, yeah, it's zero. Yeah, here it coincides. Actually, the line of action goes through the axis of rotation, and that's why the smallest distance between the two is zero, and that's why your torque, yeah, the torque, which is force times distance, will give you zero as well. Yeah. So the torque is zero. Okay, the one on the right hand side is different. This is your force here, and this is the line of action, and this will be the smallest distance. Yeah, this is perpendicular to the line of action. Okay, so this will have some torque. Torque is not zero, it's bigger than zero, and basically you have a torque in this direction, yeah, because the force is in this direction upwards, and your torque will be what we call this counterclockwise. Yeah. Okay. And this give you more details in for the mathematical equation. Yeah. Okay, but yeah, I think your trigonometry is still good enough, right? To determine if you got R here, and well, it's the theta it used is over here, yeah, between this the radius and the line of action. So if this is theta, this angle will be 180 minus theta, and yeah, so this distance, the smallest distance, will be R times sine this angle, which is 180 minus theta. Okay, and if you check the trigonometrical identity, the sine 180 minus theta is also equal to sine theta. So this is the simplest form to calculate the torque for this scenario. Okay. Okay. What is it? Showing anything? Oh, there's nothing there. Right. So okay, now for the work for linear motion, work is defined as the application of force through a distance. Yeah, just given by this, the integral of f dr give you the force. Yeah, if the force is constant, if this force is constant, then you can take it out of the yes, you can take it out of the integral, and then yeah, if the force is constant, you have f times integral dr, which gives you f into r. Okay, just this. Yeah, if the force is constant. Right, and so this will simplify the equation, and then so work is just simply F times R. Yeah, the force times the distance through which the object has moved. Okay, and similarly for rotational motion, then we have the work is equals to these equations. Yeah, F is analogous to torque in rotational, and the R, which is distance, is theta, which is the angular distance here. Okay, and the unit of work is joule. Yeah, I think you are all familiar with this, right? Okay, and then next one is power. Yeah, okay. What is power? Power is the time derivative of the work. Yeah, so the W, which is work by dt, and then you can substitute this W with Fr. Then you have this. Yeah, Fr. We got it from the previous slide. Yeah, that W is equals to this. And okay, what do you do with this one? So you've got dfr by dt. Again, if the f is constant, you can take it out of the derivative, yeah, component. So you've got f dr by dt, and dr by dt itself is speed, yeah, and that's why you got this pf. Yeah? The time derivative of the distance is velocity. Okay, so p is equals to force times speed. Yeah, which is P itself is power, right? That's for the linear. Okay, and the one for the rotational is the one and the below here. Okay, so it's very similar. And again, if you follow it step by step, you can see that it's basically we just now again the analogy of force in rotational is torque, and that's why we've got torque here, and speed we've got angular speed. Yeah, so it's very similar. I.e., if you remember the equation for the linear, then you can easily derive the one for the rotational. Yeah. Okay. There's some explanation apparently there. Yeah. Yes. The rate of doing work or the change in work per unit time. Yeah. The time derivative. Okay. Yeah. With this sharing, I cannot really see what's going to show, and after I click the button. And okay, the unit of power is watt. Okay, and then again you will see kilowatt or megawatt, but basically it's watt. Yeah, it depend. The kilo and watt is only mega, the range or the magnitude. Right. Okay, and it's table here show us the comparison between the two types of motions, linear and angular. Yeah, I think it's quite straightforward. The the last one is the mass. Mass you've got for linear, and for angular you have moment of inertia, and the symbol for it is J. For example, what is the Newton equation for force? What is the relation between force and the mass?
Higher force, higher mass.
Sorry, say that again. Force equals to
ME.
M. Yeah,
Time acceleration.
yeah, okay. There's a sister also answer in the chat box here. F equals to ma. So what do you think will be the equation for the rotational? The torque equals to what?
Equals to inertia times angular acceleration.
Yes, times the angular equation. Yeah. Okay, so you can see the usefulness of knowing the linear. You can then derive the equation for the rotational, right? Okay, I think yeah, that's all for the motions. Yeah, and then the next section we are going to look at on the magnetic physics. Okay, any questions before we move on to the next one?
So far, so good.
So far so good. Yeah, you're not sleeping yet.
I know.
I cannot see your faces, so like talking to a laptop. Well, I'm talking to a laptop. Okay, now magnetic field is the fundamental mechanism in electrical machines, and that's why we need them. We need to know it, yeah, as the basic knowledge. Yeah, and there will be 4 basic principles that are used in electrical machines. Yeah, 4 magnetic field principles that are used in electrical machines. So the first one is a current carrying wire produces a magnetic field in the area around it. Yeah. So if you have a wire and then you drive a current through it, yeah, magnetic field will be generated around the wire. Okay, that's basically Ampere's law. We'll go through this in more details later on. Yeah, each of this. Okay, and the second one, a time-changing magnetic field induces a voltage in a coil of wire if the field passes through that coil. Okay, again, a time-changing magnetic field induces a voltage in a coil of wire if the field passes through the coil. Yeah. So if you got a magnetic field and then you put a coil inside the magnetic field, if the field is changing, yeah, not constant one, then some voltage will be induced in the coil. Yeah, and this is basically the principle of a transformer, and this is Faraday's law. Okay, you need to pay attention to the underlined words here, the time changing, i.e. the magnetic field has to be changing with time. If it is a constant magnetic field, then no voltage will be induced in the coil. Okay, and that's why transformers only work with AC. If you apply DC in the input, you will get nothing at the output. Yeah, transformers only work with AC. Okay, and the third one, a current carrying wire in the presence of a magnetic field has a force induced on it. Okay, so you've got a magnetic field, and then you put a wire in that magnetic field, then you drive a current into that wire, then a force will be induced on that wire. Yeah. Okay, and if we use it smartly, then we'll be able to create rotational motion, and that's why a motor can work. Yeah. It's working based on this principle. Okay, So some force will be generated. It acts on the coil, and yeah, if the coil is wound on a platform that can rotate, then the force on the coil will then convert into a torque, which will then rotate this element, yeah, around the axis. Okay, that's basically how a rotational motor works. But also take a note that some motors are actually linear motors. You have also linear motors, and this is as well the basic principle how it works. Okay, and the last one, a moving wire in the presence of a magnetic field has a voltage induced in it. So this is the opposite to number 3. Yeah, you've got a magnetic field, and then you move a wire in it, then a voltage will be induced along the wire. Okay, and this is the basic principle of a generator. Right. Right, and then the production of a magnetic field, we are going to look at the relation between magnetic field and current in here, yeah, because this is the important principle behind or underlying the electrical machines. Right, production of magnetic field by a current is governed by Ampere's law. Yeah. So highlight here, production of magnetic field by a current. Yeah? So you can generate magnetic field by using current. Yeah? Okay. For any, this is what the Ampere's law say. Yeah? For any closed loop path, the sum of the length elements times the magnetic field intensity in the direction of the length element is equal to the electric current enclosed in the loop. And this is the mathematical equation for it. Yeah, it's maybe a bit confusing, but if you look at the mathematical equation, and then later on we're going to simplify it, that statement or that law can be written as such. Yeah? The loop integral of H, which is the magnetic field intensity around a loop, yeah, is equal to I net, which is the current. Yeah? So from here, you can see straight away that there is a relation between H, which is the magnetic intensity, and the current. Yeah? Okay, and okay, to better understand the meaning of this equation, let's us look at the following slide, the next slide. Okay, on the right hand side here, if you look at the illustration, you've got a rectangular thing here, which is actually a ferromagnetic core. Yeah, and the shape is commonly used in transformers actually. Yeah, so it's basically a rectangular core that is made of ferromagnetic material. Yeah. Ferromagnetic material means that it's easily magnetized. Yeah, it's and then it can retain the what we call the magnetism easily, yeah, compared to non-ferromagnetic materials. Okay, now we have this core, and then here you see that we've got some windings here of coils. Yeah, of coil. So we've got a coil with n number of turns. Yeah, n number of turns. Right, and then we drive current into the coil. Okay, so coil is flowing through this sorry, the current flow is flowing through this coil. Yeah. Okay, because the core is ferromagnetic, all the magnetic field produced by the current will remain inside the core. Right, this wire will generate the current that flowing inside the coil will generate magnetic field. Yeah, if you like, if you have a coil like this, yeah, if you look at the screen, you'll get a magnetic field in this direction, basically. Yeah, something like that. Okay. But here, because the coil is wound on a leg of this ferrite core, a ferromagnetic core, the magnetic field generated will tend to stay inside the core. If you imagine like the electricity current, if you connect, if you have a battery, then you've got a piece of wire. You connect the positive and the negative terminal of the battery by using that wire to create a closed loop. Current will start flowing, right? Electrical current will start flowing. But if you remove the wire from the battery, you disconnect the wire from the battery, the current will stop flowing. Is that correct? Yeah.
Yes, sir.
Why is that? Why the current stop flowing? Or if you replace the wire with a, let's say a piece of plastic, and then with the piece of plastic you connect the positive and negative terminal of the battery, will you get electrical current?
No.
No, yeah. You've got a battery. If you look at the slide, let's say you've got this battery, and then you connect it with a piece of string made of plastic, for example. Yeah, you say that the current will not flow. Yeah. Why? Because basically the resistance of the plastic string is too high. Yeah. It's so high, so you can say that the current is very close to zero. Nothing will be moving. No electrons will be moving. So in a very similar concept, this ferrite, the magnetic field also, or magnetic flux will also flow inside this core here. The coil will generate magnetic field, which then generate this magnetic flux. The flux will stay inside the core, so none of them, almost none of them, will flow outside, will escape outside into the air. Why? Because this ferromagnetic core presents itself as a low resistance to the magnetic flux, in the similar way as a copper wire presents as a low what they call low resistance, low resistance path for the electrical current. So they work in a similar way, for both this electrical current and the magnetic flux. Okay, so because almost none of the flux, none of the magnetic fluxes escape to the air, then we can assume that all of it stays inside the core and flows in this manner. We can assume in this, this will be counterclock. Sorry, this is clockwise. This is clockwise. Like, okay. Let's read again the second point here. Because the core is ferromagnetic, all the magnetic field produced by the current will remain inside the core. So the path of integrations of Ampere's law is the mean path length of the core. Okay, if you look at again this equation, this is the one that we got from the previous slide. And because the H, the magnetic field intensity is constant, we can take it off the integral, and we are left with this. Okay, the H is the same anywhere in the core, so we are left with the H loop integral of dl. But the loop integral of dl will give you basically, again, if you look at the core on the right hand side, I delete this one first. So the closed loop integral of the L, which is the length, the element length, should give you this length here, which is the mean path. Again, this is approximation, yeah, not in reality it will not be exactly that. Okay, so this this distance here is then what we call as this LC. Okay, and remember the original equation was closed loop integral h into dl equals to I, and that's why we've got this I here, which is I net. And the I net is the current that flows into the loop. Yeah? And this is the loop. And so the current will be the magnitude of the current multiplied by the number of turns. Yeah. So that's your I net, because the number of current that flows into the loop will be equal to N into I. Yeah? And therefore, then you have this equation here, down here. HLC is equal to Ni, which is nice, easy equation. Yeah. And again, this shows us the relation between the magnetic field intensity, yeah, and the I, the current. So from here you can see how the relation between the conversion from electrical current into magnetic field. And but also by using the equation, you can tell later on, you can use it as well the other process, which is from H. Yeah, if you H have a magnetic field intensity, then you can generate current. Yeah? So this works both ways. Okay, and therefore the magnitude of the magnetic field intensity in the core due to the applied current is equal to this. Yeah, this is the so which means that what do you have to do with the current if you want to increase the magnetic field intensity?
Increase.
Yes, you need to increase the current. So if you increase the current, the magnetic field intensity will be higher. Yeah. And later on, we will see that the amount of torque generated in motor depends on the H, yeah, depend on the magnetic strength, and therefore you can increase the torque of the motor by increasing the current that you apply to the motor. Yeah. And later on also we'll learn that it's not the voltage. Yeah, increasing the voltage doesn't always mean you increase the torque of the motor, but you need to increase actually the current. Yeah. This is a very important understanding. So later on when you want to work with motors. Yeah. So again, torque depends on current, not voltage. Okay, Ni is also known as magnetomotive force. Magnetomotive force, MMF. Yeah, and the symbol is this. This is like a Greek letter of F. Yeah. Is it? I'm not sure. But yeah, it's a. I just call it curly F. Yeah. Right. So this and this the name itself should reminds us of EMF, yeah, which is equal to voltage. Yeah. Later on, we'll see the analogy between of magnetic field circuit and electric circuit. Yeah. But you can see that MMF is a similar name to EMF, and they work in the same way as well. Yeah. Later on, we'll see. Okay, so this is Ni. Yeah? So again, for MMF, you can increase it by either increasing the I or increasing the number of turns, N. Yeah? Okay, magnetic field intensity H is the sense or measure of the effort that the current is putting into the establishment of a magnetic field. Yeah? So how much magnetic field that a current can give. Yeah? Then the relationship between the magnetic field intensity and the resulting magnetic flux density B within a material is given by B is equal to this magnetic permeability, yeah, into H. Okay, mu, yeah, that's the name that I was looking for. Mu into H, yeah, B equals to mu into H. Okay, H is magnetic field intensity. The unit is ampere per meter. Mu magnetic permeability, it's Henry per meter, and then the B is Tesla, or T, is capital T. All right, and then there is a mu naught here, permeability of free space. Yeah, mu is equals to mu naught into mu R. So, for example, the mu of steel, or the magnetic permeability of steel, is equals to mu naught, which is the permeability of free space, times mu R, which is the relative permeability of the steel. Yes, so this is just to make it easy for us to do the calculation, because we make it relative to this number here. Mu naught is equals to 4 pi times 10 to the minus 7. 4 pi times. I think it will be on the next slide as well. Right, and then permeability itself is the measure of the ability of a material to support the formation of magnetic field within itself. The higher the number, the easier it is to be magnetized, yeah, and to create a strong magnet as well. So that's why and you can see here, the higher, if you look at the equation, B equals to mu H, if you want to generate high B, either you have high H or mu. Yeah. But this is the reason why in electrical machines you use ferrite material for the core, because ferrite has got very high mu. We are talking about 1000 or more. Yeah. So it's 1000 or more easily magnetized compared to the free space or the air. Yeah. Air, the permeability of the air around you is very close to mu naught. Or you can just say it's equal to mu naught. Yeah. Safely say it's equal to mu naught. Okay, but when you choose like a steel, the mu itself is 1000 or more, so it can then give you a very high magnetic flux density B. Right. Okay, the H does not depend on the material. Yeah, it's just if you look at the previous equation, it just depends on the current that generating it. But the B depends on the material. Yeah, if you use steel, then the B will be a lot higher compared to if you use air, for example. Yeah, if you have a coil with a ferrite as the core, compared to a coil with air as the core, then the B for the coil with the ferrite as the core will be a lot higher. Yeah, significantly higher compared to the coil that has air as the core. Okay, this one, the one that I presented on the previous slide, the mu equals to mu R into mu naught. Just rearrange it. That mu R equals to mu over mu naught. Okay, the total flux in a given area is given by flux into this closed loop area, closed loop integral of B into dA, and dA is the differential unit of the area. And if we, for this particular example, yeah, for the ferrite core that we have, then we can simplify this equation into this. Why? Because the B is assumed to be constant throughout the area. So if you look at the ferrite core diagram, the B here or the B there on the top, on the right, at the bottom, they are all the same. Yeah. Again, assuming that there is no flux escaping into the air, so the B is all the same. Yeah. The flux is always the same anywhere, and because the area, the cross-section area, are the same. Yeah. At all these different sides of this core. Okay, So because B is constant, it's the same. So this we can simplify this into B times A. Right. Okay, and then B is equals to mu H, and then the H can be substituted or replaced by the equation that we had on the previous slides, which is this here. Sorry, this is H, yeah? Ni, which is MMF, magnetomotive force, divided by LC. And therefore the flux, this is flux, yeah? This pi is the symbol for flux, equals to mu Ni A divided by LC. Okay. So all these parameters that will define our flux. So if you want to have high flux, you can increase the area, you can increase the current, or the N, the number of turns, or the magnetic permeability of the material. So you use a material with higher magnetic permeability, and but you need to reduce the LC if you want to increase the flux. So for example, if you have for this ferrite core, you can make it smaller if you want to increase the flux in the system. Okay. Right. Okay. Okay. We still have a few more minutes. Let me just quickly check what do they have in here. Okay, let's just quickly go through this. Maybe not in so much detail. Then we finish our session today. Okay, magnetic circuit model. This concept or this model follows the ideas that we have for electrical circuit. Yeah. So your knowledge on the electrical circuit, yeah, the Ohm's law, for example, is will be very useful to understand this as well. Okay, the magnetic circuit model is often used in the design of electrical machines. Yeah, so to do the calculation, you can use this. Yeah, basic calculation. Although nowadays you can also use software, modeling software like ANSYS, yeah, 3D, sorry, finite element software to do the analysis. Okay, and the current in a coil wrapped around a core produces a magnetic force in the core. We've learned this already. This is in some sense analogous to voltage in electric circuit, sorry, or EC, producing a current flow. Yeah. Okay, so if you remember, you've got ferrite core, you have a coil, you supply current to this, then magnetic flux starts flowing. Okay, this is very similar to electric circuit. You've got a battery, and then you've got a closed loop, yeah, closed path made of conductive wire. Then current will start flowing as well. Yeah. So this will be analogous to this coil, and the flux is analogous to the current. Yeah. Okay, so in the electrical circuits, we have this equation, this Ohm's law, V equals to IR. V is the voltage or EMF, yeah, the drives current I. And very similarly, yeah, in magnetic circuits, the corresponding quantity in the magnetic circuit is called MMF, that drives flux. Yeah. So this is related to this, and the current related to the flux. So a very similar model. Okay, and the MMF is measured in ampere turns because it is equal to N times I, and is equal to effective current flow applied to the core. Yeah. MMF is equals to N times I. Okay, and then let's finish this off. A couple more slides. Right. Okay, this illustration again similar to what I've drawn in the previous slide. So in the EC, we've got V equals to IR. In the magnetic circuit, you've got MMF equals to flux into R as well. R here is a kind of magnetic resistance. Yeah, in electricity you've got resistance. Here it's a magnetic resistance, but we've got special term which is reluctance. Yeah. Basically, it's the same thing, magnetic resistance. The higher the reluctance, then the lower the flux flowing in that particular object will be. Okay, the relationship between voltage and current is similar to that between MMF and flux. Yeah. So again, if you look at these two cases, they are very similar. Yeah. And then, just like in EC, conductance is reciprocal of resistance. In MC, permeance is the reciprocal of R. Right. So this is in EC. This is conductance, and this is yes, resistivity. Okay. Yeah. And then similarly for the what do you call for the magnetic circuit, the flux can be expressed as flux into what we call this here MMF into permeance. Permeance is this. So we've got something similar here, that the permeance is equals to 1 over reluctance. Okay, permeance is equals to 1 over reluctance. Yeah. And then if you look at this, the flux itself as MMF equals to flux into R. Okay, and then if you rearrange this, flux is equals to divided by R. And then from here, you can substitute this R. So flux is equals to MMF into permeance in here. Okay, and again, reluctance is what you call just like resistance. Yeah, the higher the resistance, the higher the reluctance, the less the flux that you'll get. And for permeance is the opposite of that. Okay, and then why this concept also important or is useful, because then you can also what you call, sorry for this. Okay, sorry. Sorry, somebody's calling me. Okay. Right. Okay. Let me. So if you remember all the relations that you've got for resistances in time already up, yeah. But let me just finish this. For the series and parallel connections, you've got these equations here. For example, if you have R and they are connected in series, you've got R1, R2, and R3, and so on. Then the total resistance or the effective resistance will be just simply the sum of it. Yeah. Okay. And if you got parallel, then you've got this relation R1 plus R2, 1 over R2, and so on. Right. Okay. So and nicely, this can be applied to magnetic resistance as well. Yeah. The total reluctance, if the reluctances are in series, then it's just the sum of them. And for the parallel, it's just again a similar relation. Yeah. And then later on, we can use these relationships in doing the analysis for magnetic circuits. Okay, I think I'd like just to stop there. What time is it now? It's 12:49. Yeah, 1 minute left. Okay, do you have any questions before we close the session today?
No.
It's quite long. Yeah, it's not recommended actually to have a class, 1.5 hour class for synchronous. But let's see if we can do better next one I'll try to maybe simplify a bit. But hopefully you can understand what I have explained so far.
Yes, sir.
Yeah.
Yes, yes.
Yes, yeah. Okay. Alhamdulillah. Okay. Anyway, if you have any more questions, either you can ask me in the next class, or you can throw that questions in our WhatsApp group. The Italian apparently is still having problems till now. It's because they're moving the Italian from internal server to Microsoft server, and there are still problems due to the new. I mean, it's just been done. Yeah, as usual. I mean, this commonly happens, right? If you start doing something new, then at the beginning there are problems that associated with it, but later on, hopefully, inshallah, the problem will be gone. They're still working on this, and yeah, for this, then I will still try to stick to iTalim. Yeah, but if until next week it's still having problems, then I might start opening a Google Classroom. Okay, no more questions, yeah, inshallah.
No, sir.
Okay, alhamdulillah. Okay, jazakumullah. Then let's recite Suratul Asr and Tasbih Kifarah to close our class today, and then we can continue again next time, inshallah. Wal asr innal insana lafi khusr illa allazina amanu wa amilus solihati wa tawassaw bil haqq subhanakallah wa bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Okay, thank you very much. Inshallah, see you again next time. Assalamualaikum warahmatullahi wabarakatuh.